cause of death in our country today, and the number of patients that will die from this disease is only expected to rise within the next 20 years. The current standard of cancer care includes surgery, radiation therapy, and chemotherapy. Chemotherapy is inefficient because chemotherapy drugs cannot specifically target cancer cells, leading to the damage of normal healthy cells along with tumor cells. This leads to harmful side effects in patients, including nausea, hair loss, and a weakened immune system, and also leads to great discomfort and pain during treatment. Nanoscale coordination polymers have been developed by Professor Lin's laboratory to deliver chemotherapeutics specifically to tumor cells. These nanoscale particles are formulated from metal ions joined by organic bridging ligands and are very small size, so they can specifically target tumor cells due to the leaky vasculatures within these tissues. They have a high drug loading, so less nanoparticle has to be used to deliver the same chemotherapeutic effect. They're also biocompatible and can degrade easily within the bloodstream due to the Lagrange bonds between the ligands. These nanoscale coordination polymers are furthermore coated with lipids or pegylated to provide greater stability to the particle and also a longer blood circulation time. These particles are self-assembled under normal conditions using no specialized equipment. The specific chemotherapeutic that was studied is Paclitaxel. Paclitaxel is a mitotic inhibitor. It interferes with the normal functioning of the microtubules during mitosis to cause apoptosis or cell death. Paclitaxel is highly hydrophobic, so it's usually administered to patients via 50/50 cremaphore-L ethanol mixture in an IV injection, which is damaging to the heart, the brain, and the liver. Other side effects of Paclitaxel include nausea, hair loss, a weakened immune system, mouth sores, and hypotension. And here is the chemical structure of Paclitaxel. Professor Lin's laboratory has been able to deliver other chemotherapeutics using nanoscale coordination polymers before. My goal this summer was to coat Paclitaxel along with the normal lipid coat onto bare zinc particles. I hypothesized that with a Paclitaxel coating, nanoscale coordination polymers would be significantly larger than without a Paclitaxel coating with a standard lipid coat or without a lipid coat whatsoever. I also further hypothesized that cysteine, an amino acid, would be able to effectively cleave Paclitaxel from the particles, triggering the release of the drug, more effectively than it would be able to trigger the release of zinc from the zinc particles. Here's the method that was used to formulate the nanoscale coordination polymers. 1 aliquot of a surfactant was mixed with DOPA, which is here, and to another aliquot of surfactant was added zinc nitrate, which provided zinc ions. These 2 aliquots were then mixed together and stirred for 30 minutes, and this was then centrifuged 3 times and resuspended in 20 milliliters of tetrahydrofuran. These particles were then pegylated, again, to provide greater stability and a longer blood circulation time. 3 lipids, DOPC, DSP-PEG, and cholesterol were mixed together, along with cholesterol Paclitaxel, and added to an aliquot of zinc particle suspension. This was then dripped into 30% ethanol, stirring at 50 degrees Celsius in order to pegylate the particles. To measure the size of the particles, I used dynamic light scattering, which is a technique that measures the change in wavelength of a light and uses that to extrapolate the diameter of each particle. I also use transmission electron microscopy images to qualitatively analyze the size of particles. To measure the release of particles, I filled a dialysis bag with 6 milliliters of particle suspension and put that in a 5 millimolar cysteine solution, which was stirring at 37 degrees Celsius, as you can see in this setup displayed above. At routine time points, 1 milliliter samples were removed from the cysteine solution and replaced with 1 milliliter of fresh cysteine solution. These samples were then later analyzed for Paclitaxel and for zinc concentration. To measure Paclitaxel concentration, standards of known Paclitaxel concentration were made in 30-70 methanol PBS and their absorbance at the peak wavelength was measured using UV-vis spectroscopy. The concentration and absorbance were plotted to form a linear trend line, and once the absorbance of the unknown samples at the same wavelength was measured, the equation of this trend line was used to measure or to find the concentration of the unknown samples. The concentration of zinc within each solution was measured using inductively coupled mass spectroscopy. Here's a graph showing the light intensity percent by the diameter of each group of particles: bare particles, pegylated particles, and pegylated particles with paclitaxel. As you can see by the graph and by the z-average sizes listed in the table below, bare zinc particles were the smallest, followed by the pegylated particles, and the pegylated particles with paclitaxel were the largest of the three groups. We also measured the average polydispersity index, or PDI, of the three groups. This is the measure of the variance of the size among each sample of particles. And as you can see, that appears to increase with the addition of lipids and paclitaxel. And this suggests that perhaps adding lipids and paclitaxel increases the probability of aggregation within the particles, leading to greater variance of size. Here are transmission electron microscopy images of the three groups of particles: bare zinc particles, pegylated zinc particles, and pegylated zinc particles with paclitaxel. And these images were taken to provide a qualitative analysis of the size of each particle. Here's a graph showing the percent of paclitaxel released over 6,000 minutes, or 100 hours. By 100 hours, or the end of the study, 49.22% of the paclitaxel had been released into the cysteine solution. As you can see, the percentage of paclitaxel appears to increase, then decrease, then increase linearly. The increase at the beginning is probably the UV-vis machine picking up the absorbance of the lipids, the other lipids that were released into the solution, and which these lipids then probably crashed out of solution, and the linear release is most likely the paclitaxel. Here's a graph showing the percentage of zinc released over time into the cysteine solution. After 100 hours, or 6,000 minutes, 0.05% of the zinc had been released into the solution. To conclude, pegylated nanoscale coordination polymers are significantly larger than unpegylated particles, and pegylated nanoscale coordination polymers with paclitaxel are significantly larger than both bare particles with no lipid coat and particles with standard lipid coat. This is probably because the other lipids in the coat have long hydrocarbon tails, which allow them to form a layer more easily, while paclitaxel does not. It has a more bulky chemical structure. After release, we found that cysteine is able to cleave paclitaxel more effectively from the particles than it is able to cleave zinc. By 100 hours, almost 50% of the paclitaxel had been released from the particle, while only 0.05% of the zinc had been released. This result is probably due to the placement of the two within the particle. The zinc is covered by a lipid coat, surrounded by a lipid coat, and paclitaxel is part of that lipid coat, making it easier for the cysteine to cleave the paclitaxel. I'd like to acknowledge Professor Wenbin Lin and Christina Chan of Lin Group for guiding me and allowing me the opportunity to work with them this summer. I'd also like to thank all those who put together the CURE programs, specifically Drs. McKinda, Dolan, Goss, and Michelle Demecki. And I'd like to thank Mr. Wolschlager and Mr. Pintz of Hinsdale Central High School for organizing the Scientific Inquiry and Research program at that high school. Finally, I'd like to thank all of you in the audience for allowing me to present.